This is the first video for Chapter 13 in McGraw-Hill, which is gases. So last chapter, we talked about kind of the background of gases. We actually dealt with Graham's law and Dalton's law, which we're going to cover again in this chapter. We're going to start a little bit differently here because I start with a combined gas law, and sometimes people hit that as the last one, but I think it makes much sense to have it as the first one since it has all the parts we're going to be talking about. To give you a little bit of a start, most of this chapter, I'd say about half of this chapter at least, is going to be math. The other half will be concepts and terms. The math's going to be a little different. It's not going to be like the dimensional analysis we've had in most of the other chapters. It's going to be formulas, and I'll give you the formulas. So really, this is just plug and chug. You just find the formula that has the things you need, plug in, and solve for the one thing that is the unknown. So we're going to start out talking about the variables. We'll be talking about pressure. P is pressure, V is volume, T is Kelvin temperature. Very important point. Every temperature in this chapter will need to be Kelvin when we deal with it. So C to K, add 273. Remember, when you go up the alphabet, C to K, you add 273. So we shouldn't be subtracting 273 on anything in this chapter, just adding. There's also going to be the letter N, the lowercase n, which is number of moles. So that deals with the quantity of gas. Whenever you have mole or mass in an equation, you know you're going to need that N because the N is number of moles, and that can be translated to mass. So we're going to start out by talking about the combined gas law, which is P V over T equals P2 V2 over T2. And you might think to yourself, what is all that stuff? It's like alphabet soup. But keep in mind, all it's saying is that we have an original pressure, volume, and temperature, and then we change something. And when you change something, everything else changes a little bit. So this is the new pressure, the new volume, and the new temperature. Remember, the temperatures are always Kelvin. So in problems, think about this. So here we have the original situation. We've got a volume, and let's say this says about 80 milliliters, and we have a pressure, which is 1 atmosphere. We'll just assume it to be 1 atmosphere because we've opened this little container, and the air pressure today is actually 1 atmosphere. So we're kind of in between stormy and blue sky day. Just happened to be about 1 atmosphere. And then, of course, the temperature, it's 20 degrees Celsius in this room, a little chilly, but remember that's Celsius. It's not Fahrenheit. 20 Celsius, so that would be 293 Kelvin. Those are our originals. Let's do something. Let's throw it in the microwave and heat it. Well, so we're going to heat it 100. So we had 293. We heated it 100 Kelvin. Now we've got 393. What's that going to do? It's going to change some things. When you heat this, if the cylinder can move, what's going to happen to the plunger? Obviously, the molecules are going to move more. They're going to have more collisions, and it's going to cause this to get bigger. You heat it, it's going to spread out, expand. Okay, now, what if we tape this and it couldn't expand? Well, when you heat it, then it's going to get more pressure. So you can see how all the things new over here are going to be different. That's all this is. It's original pressure, volume, temperature, and then new pressure, volume, and temperature. And what I recommend you do on every problem that you do is to write all these, PVT, P2, V2, T2. And then maybe N if you have something with amount of gas. And then you write what you've got in the problem. And sometimes some of these things are going to go away. Let's show how something disappears or goes away mathematically. So let's say that the temperature was held constant. Let's say that it was 100, okay? That's 100 Kelvin. And this one was 100. If they're 100 and then it stays 100, well, we could get rid of that mathematically because if I multiply both sides times 100, that goes away. But you have to multiply this side times 100. Or if you want, you can Anderson swap it up. Either way, you're going to end up with 100 over 100. Anything over itself is 1. 1's the identity in multiplication and division, so it goes away. If something is not mentioned in a problem, then consider it to go away. Now, we don't just say it goes away, but mathematically we've just shown that if there's a constant value, it is 1, which mathematically disappears. So, if something's not mentioned in a problem, or it says it's held constant, then you can get rid of that. In this case, we've got pressure times volume equals the new pressure times the new volume. And that's it. We didn't have to worry about temperature. So, very important concept mathematically. If a value is constant, then it ends up being 1, divides itself away or multiplies itself away, and it goes away. Very important math concept. So it says that when a value is held constant, mathematically it goes away or cancels. So that's our combined gas law. And the reason it's called combined gas law is because this is put together by several chemists and physicists who did research, and they discovered parts of this. And then later on, they found out, well, wait a minute, your part and this part can go together, and that's why it's called the combined gas law, because it has pressure, volume, and temperature. So we're going to move on, and specifically, now we've got some of the different gas laws, and you need to know these gas laws. I will ask you some questions about them, and you should be able to state the gas law in a sentence or two, or write the equation that corresponds to it. And the easiest way is to learn the way I'm going to tell you to learn these, learn the formulas, and then figure out, well, if something's a ratio, it's direct proportion. If it's multiplied, then it's indirect. We'll see that here in a second. Start out with the combined gas law. Combined gas law has PV over T equals P2V2 over T2. It's everything. Think of private, PV over T. PV over T. Boyle's gas law. We just did Boyle's gas law. We canceled the temperatures. So how would we state Boyle's gas law mathematically? Pressure times volume equals the new pressure times the new volume. How would we state it in a sentence? Well, there's a little bit of a trick to this. When you multiply two variables and then you multiply the two new variables, that is an indirect proportion. And we can show that mathematically because we end up with the pressure 1 and pressure 2 are diagonals when we set it up as a ratio. But when they're multiplied like Boyle's law, it's indirect. So here's how we say it. Pressure and volume are indirectly proportional when temperature is held constant. We know temperature is held constant because it goes away. Second one, how do we remember these? Well, I've got ways to remember them, and about 3/4 of people latch onto these and say, oh, that's cool, I can learn that. And some of them complain and say, that's too corny. Not a problem. Learn it the way you want to do it. But all of you have probably made macaroni and cheese, or at least boil water. So let's say that we're making macaroni and cheese, and we go in the other room to watch the Cowboys lose. I'd say play, but this year it's been lose. We come back and, we hear this noise. Shh! We forgot about the macaroni and cheese, and it was boiling over. So way to remember that is that you're peeved. Peeved means you're mad. PV is peeved because it boiled. PV, peeved, because the water boiled. Okay, it's corny. Charles' law. Charles' law is this V1 over T1 equals V2 over T2. Tell me what's held constant there. Okay, that's a rhetorical question because you're watching the video, but obviously the thing that disappeared was pressure. When it's a ratio, V over T equals V2 over T2, and it's not crisscrossed, okay, so V's are on top and T's are on bottom, and they stay that way, then it's a direct proportion. Because if one increases, the other increases, temperature and volume. And that makes sense. Remember this plunger, I throw it in the microwave, crank it up for a minute. What's going to happen to the volume when the temperature goes up? Well, temperature goes up, the molecules hit harder, volume increases, and it may even just pop open. Okay, and that makes sense. You know that volume increases when things are heated. So volume and temperature are directly proportional when pressure is held constant. It's not that hard to remember this. How do we remember Charles' Law? Well, some of you probably watched Charlie Brown. Charlie Brown, you probably watched it on TV, maybe especially during the holidays. So Charles on TV, we're using T and V, V over T. And, when you look at it, you say, well, how do I remember that it's V over T? Well, one is I'm going to give you the combined gas law. And if the pressure is held constant, it goes away. Basically, it's just a combined gas law without pressure. So it's easy to write. So we move on. Graham's law. Back up. Dalton's law. We covered Dalton's law in the last chapter. It's one of the easiest one. Dalton's law is basically that all the parts add up to the total. All of the parts, like the different gases, all of their pressures add up to the total pressure in a container. Now, you'll be given this one of two ways. You'll either be given 2 or 3 parts, what's the total, or you'll be given the total and maybe 2 of the 3 parts and say, what's the missing gas pressure? Pretty easy stuff. Most of you thought so in the last chapter anyways. Graham's law, you remember that? We did that in the last chapter. Graham's law, you will use Graham's law anytime you're talking about effusion, which is the movement of a gas from a container where it's concentrated through a tiny opening out into the space outside, or diffusion, which is the movement of a gas from a highly concentrated to a less concentrated area. That's like perfume spreading out in a room, or ink drops spreading out in a little bucket of water. Anytime there's a question about how fast is this molecule compared to that molecule. In the last chapter on the test, we had like a little tube, and it said we released these 2 gases. Where are they going to meet? Well, you had to figure out which one was fast and which one was slow. The slow one's not going far. The fast one's going to, be all the way over on the other side. So they met close to the big one because the fast gas moved fast, or the small gas moved fast. All right. Then we talk about the ideal gas law at the end. The ideal gas law. Remember, I told you about the letter N, the lowercase n. This is the one that contains the N, which is how many moles of gas. Any problem where you have a question about moles or grams of gas, you're going to have to use the N value, which PV equal nRT. So you know P, V, T, and N. What's R? Well, R is an ideal gas constant. And it can be given to you in either atmospheres and millimeters of mercury. So the different pressures have a different R value. Because when that one thing changes, you already know when the pressure changes different units, the number's different. It's like 1 foot is 12 inches. Well, it's the same value, but the numbers are different because we have different units. Okay, so there are several R values, and those are going to be given to you in your possibly useful page. You might ask, well, why is there a constant? Well, let's think about this. P, V, over NT equals R is a way we can write this. You Anderson swap the N and the T down, and you end up with PV over NT equals R. Let's think about this. When you change the amount of gas, what happens? Well, one of 2 things. Either the volume is going to get bigger, or if the volume can't get bigger, the pressure is going to get bigger. If you put more gas into something, there are going to be more collisions, more pressure. So that's the deal, is that they found out when they made this bigger, one of these things got bigger, and it counterbalanced. What about temperature? Well, when we made the temperature bigger, either the pressure or the volume gets bigger, or both, and they counterbalance. So no matter what we change on this, it balances itself out, and it always equals that same value, a constant. And those R values, like I said, are always the same. Because every time you change something down here, something up here adjusts so that the value still maintains a constant. And that's the R value. Okay, now, the other thing is, besides these gas laws, I'm going to want you to be able to tell me the gas laws using just common sense. So, I take this, I tape this, and I throw it in the microwave. What gas law are we representing? Well, we're going to throw it in the microwave and increase the temperature. And since the plunger can't move, what's going to happen to the pressure? It's going to increase. Okay, pressure and temperature. which is a gas law called Gay-Lussac's law. Pressure and temperature are directly proportional when volume is held constant. I held the volume constant because I duct taped this and it couldn't move. And if you remember these gas laws, I will give you the combined gas law, and the other gas laws, most of them are pretty much just something held constant and something goes away and it leaves the rest, like for Charles' law it's V and T, for Gay-Lussac's law it's P and T, and for Boyle's law it's P and V. So, if you look at the combined gas law, you should try to get that to where you could make the other gas laws just by holding something constant. That doesn't take a whole lot of math work. All right, we're going to move on. So here is the ideal gas law, and here are all of the different R values. And like I said, I'll give you those R values. There are some other things over here that maybe will help you understand the units. 1 atmosphere is 101.32 kilopascals. So the R value when we have liter kilopascal mole Kelvin is 8.3145. Same thing as joule per mole Kelvin because it's really the same unit. What about if we have R value with calories? Well, it's totally different then. It's like 1 foot is 12 inches. Totally different numbers, but they're still equal. Okay? 1.987 calorie per mole Kelvin. And then what if we have liters per millimeters of mercury over mole Kelvin? Notice that it's just the pressure unit that's changing on each one. That value is 62.364 millimeters mercury per mole Kelvin. So anyway, those are the different R values, and you just basically look them up and plug them in. That's how you're going to use those. So you pretty much always know R. It's one of your constants that you'll know. Avogadro's principle. We covered Avogadro's principle back when we studied the mole, but we're going to kind of review over this again. And you should be able to state Avogadro's principle. It says that equal volumes of gas at the same temperature and pressure contain the same number of particles. So the idea is, if you remember, that it doesn't matter whether we have big gas or little gas, it takes up the same volume. Here's a big gas, it moves slow. Here's a little gas, it moves fast. They take up the same amount of space. The big one doesn't have to move as fast because it's big. The little one moves fast, and that makes it take up the same amount of space. So it doesn't matter what gas we have, each molecule takes up the same amount of space. So if we had 100 of these, if we have one of these and one of these, they take up the same space. If we have 100 of these and 100 of these, they take up the same space. If we have 1 mole of these and 1 mole of these, they take up the same space. And we call that the molar volume, which is 22.4 liters at standard temperature and pressure. So the whole idea here is that if we have equal volumes at the same temperature and pressure, they have equal numbers of particles. And that goes all the way down to 1 and 1 here. This moves slow, this moves fast. They take up the same amount of space. 1 molecule, 1 molecule. Equal space. So, that goes all the way up to a mole or even bigger. And that's what Avogadro's Avogadro's principle says. If we have an equal volume, like 1 liter of oxygen and 1 liter of hydrogen, at the same temperature and pressure, they have the same number of molecules. STP is standard temperature and pressure. The conditions are 0 degrees Celsius and 1 atmosphere. And molar volume is 22.4 liters. Just so you know that that is that quantity. And that's the quantity that you'll be given. All right, so ideal gas law continued. There are a few other versions of this, and you'll get these on your possibly useful page. PV equals little m over big M. Little m is the mass that you're given in the problem. Big M is molar mass times RT. Since N, the number of moles, is equal to the mass you're given over the molar mass, that comes out to moles, we could substitute. So this way, you know the molar mass because it's given on the chart, and the mass in a problem, it may be given or you may be solving for it. So that just gives you another option. And, again, there are some of the different R values depending on what it is you're solving for. So this other formula has density in it. Some problems you may be solving for density. If you are, look for this formula. Pressure equals the density times the R constant divided by the molar mass times the Kelvin temperature. So, the whole deal on these is write what you're given, go find a formula that has those parts, and then plug and solve for the one thing you don't know. And again, all the R values there, so if you wanted those, you've got them. That finishes up this first lecture notes. Work on your review some. Good luck.